straightforward to understand, and we'll be talking about after that high-level injection, and hopefully toward the end we'll at least get close to be talking about this wonderful device called the HBT, the heterojunction bipolar junction transistor. The theory is relatively straightforward, although the fabrication is not so simple, but we don't have to fabricate them, we just have to understand how they work. Okay, welcome back. This is a kind of a broad outline of some of the topics we'll be covering today's session. We're going to start off with a bit of mathematics. Hopefully it won't be too painful when we talk about the base currents in a bipolar junction transistor. And hopefully if we get through this in one piece, we'll be able to go on to the second order effects, some of the things that degrade the performance, specifically the early voltage, the early effect, high-level injection, reduction in beta for small forward biases. And then on to the good news. We'll be covering two second-order effects: non-uniform base doping, which is fairly straightforward to implement, and then the more important one, which is the HBT, and that is relatively straightforward to understand, not so easy to fabricate. And then we'll end with a video clip, which I hope you'll find interesting, from the Twilight Zone. Okay, first let's start off with the mathematics. Okay, the base currents in a bipolar junction transistor. There are 4 injections that we'll be looking at here. The base is the important thing. What happens at the emitter and the collector is of secondary importance. The primary injection is from the, in this case of PNP, is from the emitter holes, which are emitted from the emitter into the base, and then we have electrons, which are injected from the N-type base into the emitter. Excuse me. It is the ratio of these two, which you've seen before, which determines the beta of the device. 2 secondary injections, holes injected from the collector into the base. We'll be doing a fair amount of work with this. We like it to make it as small as possible. And then this one, fortunately, it is small, and that's electrons injected from the base into the collector. One of the reasons that it is small, in fact, the main reason it's small, is because we have a negative voltage at the collector, which repels these guys. Negative voltages repel electrons. Even though the injection here is much larger than the injection here, because this is going from a relatively low doped or moderately doped into a very highly doped. This is going from a moderately doped into a low doped. So the reason that we can make this so much smaller, comes out as much smaller, is because we have a negative charge at the collector terminal. Okay, we have 2 electric fields, one pointing from right to left. The reason is I should actually have perhaps made this a little bit smaller here, because the electric field only exists in the depletion region. So there's no electric field out here. The electric field is only where we have fixed charges. We have fixed positive charge on the N side, fixed negative charge on the P side. So the electric field, the internal electric field, goes from right to left in the negative direction. And here it's exact opposite. Plus fixed charge here, minus fixed charge at the P region. So we have a positive internal electric field at this point. We define 2 coordinate systems. One, the x prime, which goes from 0 at the edge of the depletion region to x sub c, or actually it should be w sub b here, sorry about that. And then we have an X prime, which goes from right to left, and we'll be using that when we talk about injection of holes from the collector into the base. Okay, so all of that is pretty much summarized in these words here. We have 4 currents. The first one is from the holes injected from the emitter into the base. That comes from here. Then we have an electric current here. Notice that the flow of electrons goes from the base to the emitter. Therefore, the current goes in the opposite direction because these are holes, and the current goes in the same direction as the current due to the holes which are injected from the emitter into the base. At the other side is exact opposite. Hole current goes from right to left. That's here, that injection, and this injection, because it goes from electrons injected from the base into the collector, the current goes in the opposite direction. And I've labeled those 1, 3, 5, and 6. There are 2 other ones which comes from previous sessions, which we're not including here. These are the 4 main ones that we need to take a look at. Okay, so first we take a look at the case where we have a short base. So this term goes to 0, and I could either use dB, which is the diffusion constant in the base, or I could use dP, because in the base we're going to be talking about holes. Okay, so let's see. The solution is relatively straightforward. It's just linear. We have 2 boundary conditions. We have 2 unknowns. And we know that the current is going to be constant, and we can solve for that. And here it is. This is the excess carrier concentration, and the current is just a derivative. Of course, the derivative of a constant is 0, so I don't have to worry about that. I apologize for some of these W's. They should have B's in them, but I hope you'll forgive me. Sometimes I forget to put the B. Okay, now I want to make a point here. When we use an I1, let's go back here, we're talking about the current which we follow from one point, generally as a function of x, and we're going to follow this current, for example, from this point right here at the beginning of its journey until it reaches the end of its journey at the other junction. When we talk about IEP, we use letters, then we're generally talking about the current at a specific point. Here it doesn't matter in this particular case because the current is constant. So we can use either letters or numbers. And here's the current. We've seen this before, and hopefully that should be relatively familiar. Okay. So if we follow this current here from the base, inner base junction into the collector base junction at the end of its journey, we can write the current at the other end, and that we call ICP. And we can do the exact same thing, and the significant thing is we find that ICP is equal to IEP, and that just is a statement, very trivial statement, that nothing's lost. There's no recombination. So what goes in comes out. Okay, so now we take a look at, we try to tackle the general case, and for the general case, the excess minority carrier concentration, we go back to chapter 14, and this is an expression that we have here. This should be an X prime here. And again, we've seen this expression before. This represents the excess carrier concentration in the base as a function of position, in this case particularly X prime. So in this figure here, if we see that we have a forward bias, we have the collector is positive with respect to the base, then we have a reduction in the current. And if we have a reverse bias, which is VCB less than 0, that's reverse bias, negative voltage at the collector with respect to base, we have a increase in the slope of the excess carrier concentration, and that gives us a increased current. Don't forget that the current is proportional to the slope. This is low slope, not so good, not so much current. High slope, more current. And this is the equilibrium condition where we have basically a p-n junction. Okay, so now if we follow that current, basically we take this guy and we thus differentiate it. We get the derivative of the sinh is the cosh, and that's here. And we bring down some constants, but other than that, it's relatively straightforward. And we use an I1 because we have the current as a function of position. Unlike the previous case, the current is not constant. Okay, now we want to look at the terminal currents. The terminal currents are the currents that exist, oh boy, this goes all the way back, at this point right here and at this point right here. These are the terminal currents. The terminal current at the emitter base junction, the terminal current at the base collector junction. And these will be currents with subscript of letters rather than numbers. There we go. Okay. So at the emitter base junction, remember we have these two coordinate systems. One goes from left to right. That's the standard, the x prime, and the other goes x double prime goes from right to left. So let's see. Okay, yeah. So at x equals 0, that's at the emitter base junction, we simply put in x equals 0. And here, x double prime will be equal to WB, because that's the one that goes from right to left. And the cosh of 0 is 1. So that's where we get a 1 up here, and we get a cosh of WB over LB. So this is an important equation. This is the terminal current, which is composed of two currents. One holes injected from the emitter into the base. The other holes injected from the collector into the base. This one is starting its journey. This one is ending its journey. It goes all the way from the collector, the base collector, and it winds up at the emitter base junction. We can do the same thing by just flipping it around and looking at what happens at the base collector junction. At the base collector junction, x double prime is 0 and x prime is WB. Let me just go all the way back here and just make that clear again, because the first one, the IEP, is at this point, x prime equals 0, x double prime equals WB. At this point here, x prime equals WB, and x double prime equals 0. So that's really what we have here. That's all that is, and that's it. So we have IEP and we have ICP. And we'll come back to this in just a little bit. These are equations which are many times just written down in the notes. I've tried to motivate it. It's kind of a tough sell at times, but anyway, we accept them, I hope. Okay. Anyway, at this point, we just have to add the electron components. Okay, so this is the electrons. How do I know it's electrons from emitter to base? Because it's got VEB. So this is the electrons that are injected from the base into the emitter, from right to left, base, emitter. And if electrons go from right to left, that means the current goes from left to right, and that's why it's positive. This term represents electrons which are injected from the base into the collector. And if electrons go from base to collector, left to right, that means that current goes from right to left. And of course, that's why we have a minus sign here. So if we put these electron components, we have the total current from the emitter is at the emitter base junction is equal to the electron component plus the hole component. So we just add this extra term right in here, and here we're just collecting terms. So basically this is the second line is basically just the first line with some terms collected, and we can do the same thing at the collector. We have the electron component, which is right here, plus the hole component, which is this term and this term. So these two terms are from the previous equations, and all we do is just add the electron component, and that is the total current. Now let's take a look. Let's go back to 15 and 16 and take a look at the whole currents if we have saturation mode. Saturation mode is where we have someplace. Where do we have that? Yeah. If both junctions are forward biased, and we're going to say that the forward bias is the same at both the emitter base and the base collector junctions, and it's equal to V. So we just basically put that into 15 and 16, and we get immediately that they are exactly the same except difference in sign, and that exactly makes sense. The ICP is negative, it's going from right to left, and the IEP is positive, going from left to right, and the total current is 0. So while these equations, 15, 16, where are they? They may seem a little bit obtuse and intimidating, at least for one case, saturation case, they make sense, and they give exactly what they should be giving. Okay, good. So now we can look at the base transport factor, which we know is very, very close to 1. And we can take two components. We can go back to 15 and 16 and take the, I'm always going back and forth. I don't feel like writing these out again. It just takes too much effort. But we can take the ICP at the beginning of its, at the end of its journey, which is this term, and we can divide that by the IEP at the beginning of its journey. So it's end divided by beginning, and that's exactly what we're saying here. What comes out, which is the end of the journey, and what comes in, beginning of the journey. So it's 1 over the cinch, which is the ICP term, divided by the cosh over the cinch, which is the EP term, and that works out to be just 1 over cosh, as the cinches cancel out, and that is always less than 1. We can expand it in the Taylor expansion of the hyperbolic cosine, which sits right here, and we get that the base transport factor is approximately equal to 1 plus the sum of 1 plus 1/2 WB over LB, these terms right here, and assuming that all the higher order terms go to 0. And this is an equation which appears quite often in many textbooks. Okay, so just a little bit about the emitter efficiency. You can read about that. I'd like to get on to finally get on to second order effects. The first of the second order effects we'll be looking at is the early effect. It was named after the person who did quite a bit of research on it in the mid-1950s, I believe, Jim Early. So it has nothing to do with the time of day, it's just named after the person. Okay, so let's look at the standard PNP structure, 1917-15, and until this point, we've never said why the collector should be lightly doped. If, for example, we made the collector 10 to the 19th, everything that we've said up until now would be unchanged, and we would have a symmetric device. We could run it forwards or backwards, and the performance would be exactly the same. The reason that the collector is lightly doped is because we want the bulk of the depletion region at the base collector junction to fall on the collector side. We'd like as least amount of depletion region falling on the base side as possible. So we have 2 orders of magnitude in doping differential between base and collector, so that almost all of the depletion region, which is in red here, will fall on the collector side. And let's see why that is the case. Go back, and we have 2 curves here. Curve 1, which is in red, which shows a relatively weak forward bias at the base, at the emitter base junction, and a relatively weak reverse bias at the base collector junction. Almost in equilibrium. We have a bit, this is the red curve right here. We do have operation. We have a collector current. We have holes injected from the emitter into the base, and the current is given by the slope of the red line. Now look what happens when we increase the forward bias at the emitter base junction. Then this curve, or this line here, shrinks. Forward bias, the depletion region shrinks, so the depletion region now is, the edge is governed by the inner line, and if we increase the forward bias at the emitter base junction, we're generally going to have to increase the reverse bias at the base emitter junction. So what happens when we increase the reverse bias is that the depletion region expands. But the depletion region expansion is going to be mostly at the collector region. So this is with small reverse bias. This line represents large reverse bias. But there's going to be a little bit of expansion also into the base. So curve 2 represents large forward bias here and large reverse bias at the base collector. And notice what happens to the line. The line now has a much steeper slope. The current has increased, even though we haven't, well, I should say the current increased much more than we would have expected, due only to the increased forward bias at the emitter base junction, it also increases because the depletion region at the base collector junction moves to the left. So if it did not increase due to there, we would have this point here being over here, and that is not the case. The slope is now increased, the current has increased, and that is, well, first, before we show the curves, let's look at a schematic diagram. This diagram should be relatively straightforward and hopefully not too strange. This is a PNP, so we put a positive bias at the emitter, and what we're looking at here is the excess hole distribution at the junction right here as a function of forward bias. As forward bias goes up, the slope goes up, and all that makes sense with constant reverse bias. What would happen if the reverse bias would increase? This number here would fall down. At constant BC, this number here, or this level here, is constant and doesn't move. So all this diagram says is basically as we increase EB at constant VBC, there is just a forward bias boost, and we get a greater IB and a greater IC. Their ratio is constant. Of course, the ratio is the beta of the device. For the standard, quote-unquote, standard doping, it's about 100, maybe a little bit more, but not too much more. There's no recombination. How do we know this? Because they're straight lines. If they weren't straight lines, if there was recombination, they would not be straight lines. They would be at least partially have an exponential part to them. And we can see that in the output characteristics as IB goes up, which is to say as forward bias goes up, we jump from curve to curve to curve. Small forward bias, larger forward bias, and really larger forward bias. And I just noticed here, because I'm a little bit perverse, that this figure is for an NPN transistor. And how do we know that? What's the giveaway? VCE. If it was for PNP, it would be VEC. Doesn't matter. IC stays the same. So that's something that, not all that big a deal. Okay. All right. Back to PNP. Now let's hold the forward biased fixed VEB and changed VBC. So now the left side is constant. Remember over here, the left side changed and the right side is constant. Here, the left side is constant and the right side changes. So we have a constant IB. We're on one of these curves, and we just change the reverse bias, so we're moving along one of these curves. Now, for a forward bias, we would be somewheres in here. As we move into more and more of a reverse bias, the curve sort of falls over and we become more and more horizontal until we get to a point where we're completely horizontal, and as much as we increase the reverse bias, the current does not change. And that point is when we get to an excess carrier concentration of about 10 to the third, minus 10 to the third, and we've seen that before. So all that is a bit of review, but we would so we'd like to get these curves. We don't get these curves. This is not what is observed, and that's what I'm saying here. What we observe is that these curves have a slope to them, and that is because of the depletion region, and that is because of the early effect. And here is a graph which hopefully we can understand that. First, let's start at a small IB at the emitter base junction. We have a small number of excess carrier holes. We have two reverse biases, or actually three reverse biases. First, no reverse bias, which is equilibrium, which is this point right here. Actually, this point probably should be here. It really doesn't matter. When we increase the reverse bias, this point moves to here. And then at high reverse bias, it moves to here. And that is shown by, probably should have put this in different, I made this a different color. But this is low reverse bias. This is high reverse bias. And notice that the slope here is much, much greater. Not only that, the slope increase is greater for large IB than it is for small IB. And that is all summarized in this diagram right here. So instead of being horizontal, they have an increased slope. And the nice thing is that all of these lines end at one point right here. Smaller slope, smaller IB, larger slope, larger IB. Slope increases with IB such that all the points coalesce at something called the early voltage. We would like this to be as large as possible. And what's a good early voltage? Well, we found that it doesn't affect the device performance too much if we have early voltages on the order of 80 or 90 volts. So that's a goal that we shoot for. Well, you say, well, heck, isn't it nice to have larger currents? Yes, but the important thing is not how large the current is. In current here, I'm talking about IC. It's the fact that the current is controlled by IB. That's what makes an amplifier an amplifier. And for example, at this point, or this curve right here, we have too much control of the output current by the output voltage. And that's basically a resistor, and that is not ideal. And again, I remind everybody that this is for an NPN structure. Again, I could just as well put VEC and nothing would have changed at all. So the bottom line on the early effect is that in order to make the early voltage as large as possible, we want the depletion region to be as small as possible on the base side of the base collector junction. And in order to do that, we make the collector doping as low as possible. If we could go less than 10 to the 15th, then the early voltage would move to the left. If the collector doping is greater than 10 to the 15th per cubic centimeter, we would expect the early voltage would move in the wrong direction to the... Okay, the next topic is called high-level injection, and that is again a second-order effect. Let's consider our standard PNP with the standard doping, degenerately doped for the emitter and moderately doped for the base. And we can write the law of mass action. We've done this many, many times. At this point right here, at x prime equals 0, or in the bulk, we're going to start with the bulk, and then we're going to go with the depletion region edge. So in the bulk, the number of majority electrons, that's why it's NN, that's majority electrons, and 0 represents equilibrium, multiplied by the number of minority holes in the N region at equilibrium is equal to Ni squared. Ni squared, of course, is 10 to the 20th, 10 to the 10 squared. In this particular case, the NN0 is 10 to the 17th, and the PN0, therefore, is 10 to the 3rd. Again, we've seen that quite a number of times. And this area here, these next few sentences, I just expand that and basically write what I just said. Okay, so now if we apply a bias, it could be VEB if it's PNP, or VBE if it's NPN. But the law is the same if it's, or the theory is the same if it's a emitter-based junction or a PN junction. So I use the more generic term VA, where A, I suppose, applies to applied, the applied voltage. And if I apply a bias of 0.6 volts, this exponential term works out to be 10 to the 10th. So therefore, the number of non-equilibrium, there's no zero here, non-equilibrium holes in the N region is boosted by 10 to the 10th. The Pn0, the equilibrium number, is 10 to the 3rd. So the new number, the Pn, is 10 to the 13th, and that is right at the depletion region edge, right at this point, right here. Okay, now, before I go through that, that's basically what this equation says right here, 1530. It says that the minority holes at x prime equals 0 at the depletion region edge, multiplied by the majority electrons at equilibrium, and that's what we write here. The Pn0 right here is equal to Pn0 at 0 multiplied by the exponential, and the Nn0 that's here, and that is equal to 10 to the 20th boosted, so this whole number here is 10 to the 30th. I can write for Pn0 that take the right side of the equation and divide it by Nn0 at 0, which is just the doping. In this case, 10 to the 17th. That's the doping density at the in the base. Okay, all that is review. Now, high-level injection occurs when the forward bias increases, no longer 0.6, not even 0.7, not even 0.8. It's getting around 0.85, 0.9, 1 volt. It's so high so that this boost is such that the minority holes become on the order of the majority electrons. So this guy here and this guy here are about the same. So if they're the same, right here, minority holes, which was very low, 10 to the 13th, that's pretty low, becomes on the order of the majority electrons, 10 to the 17th. So these things are about equal now. So now I can basically take this guy and substitute Pn0. So it's Pn at 0 squared is equal to Ni squared times the boost. Again, this is a big number, and just take the square root from this equation right here, and I get the number of minority holes goes like the intrinsic value boosted, but there's a factor of 2. Because when you take the square root of an exponential, you divide the power by 2. Now this kind of makes sense because it's sort of a practical application of the Chatelier's principle. When one increases the bias to an extreme, nature says, hey, that's too much. I'm going to try to limit that. It's like stretching a rubber band. You stretch it, stretch it, stretch it, and it starts to react and starts to pull back. And that's what's happening here. Otherwise, there would be a runaway, the current would go crazy, and everything would be not very good. So what nature does is it limits the rate in which the holes are injected into the base for extremely high forward biases. And this is illustrated by this diagram here. For low-level injection, this number of injected, or the minority carrier concentration goes like the VEB. In very high-level injection, it goes like VEB divided by 2kT. So the increase goes down, and that is something which we see. It's observed, the model predicts it, and the model is correct. There's another way to look at that, and that is the number of electrons. So if we can, again, we have about 1 to 1.1 volt forward bias. There is no barrier. The barrier is essentially gone away. So the number of electrons here can become on the order of 10 to the 18th. Well, since there's no barrier, if I have 10 to the 18th here, I'm going to have 10 to the 18th of electrons at this point. Well, I've got 10 to the 17th electrons in the bulk. 10 to the 18th over here, 10 to the 17th over here. I have a diffusion of electrons from left to right. But if electrons go from left to right in the positive direction, it means that current goes from right to left, and that current opposes the injected holes, which also go from left to right. So I've got hole current going from left to right. That's the major current, and I've got electron current also going from left to right, and that's opposing the major, and then I have a reduction in the net current. So it's the same thing, just two different ways of looking at it, and one sees both of those, by the way, in textbooks and courses. So if we plot this thing on a log scale, this is the low-level injection. On a log scale, this would be a straight line for I sub c, and in high-level injection, the curve for I sub c, which is the hole current, the major current, kind of tips over a little bit, and that reduces the beta. So the beta here would be 100, but the beta here for extremely high values of forward bias would be much less. Okay, so one last second-order effect is reduction in beta at small values of forward bias at the base emitter junction. The high-level injection is large values, very large values of forward bias. The reduction in beta is also possible, and in fact happens, observed, at very small values of forward bias. And the idea is here that we won't really talk about this in any detail. This expression is derived in Chapter 4, and it's done in more advanced courses and many more advanced textbooks. This is the Shockley-Reed-Hall theory. I never could figure out whether it's Shockley-Reed-Hall or Shockley-Hall-Reed. The only thing you can be sure of is Shockley got his name first, because that's Shockley. He always gets his name first. Anyway, so U is the net recombination rate, R is recombination, G is generation. If the NP product is greater than Ni squared, that's non-equilibrium on the high side, there will be a tendency for recombination. Again, this is simply a statement of the Shockley's principle. Stress a system, and the system will try to reduce the stress. If you put too much charge in the system will try to reduce the stress by recombination. On the other hand, in the depletion region, where the NP product is less than the equilibrium, this system will try to generate. Well, if you look at this expression, you've got a recombination current on top of NP, which goes like Ni squared, and that would go like the forward bias of our standard value of E to the voltage divided by KT. So this guy goes like E to the voltage divided by kT, but here it's to the first power. So the first power would be just like we had for high-level injection. This would be E to the voltage divided by 2 kT, because it's the square root. So for very low values, this term predominates because we don't have enough energy to overcome the barrier, so we have a tendency for generation. And at higher levels, when we are able to overcome the boundary, we get the regular voltage divided by kT. So what happens is that for very small values, this term predominates, and as soon as we get to turn on, somewhere in a range of 0.6 volts or so, then this term begins to dominate, and then this term is still there, but it is suppressed because this thing takes precedence. And that is shown here. And for very low values, I get the same slope that I had for very high values of forward bias. So that's the complete Gummel plot for low-level injection and for high-level injection. Okay, we're going to start.